Thank you, Paul. My daughter's been getting the flu recently, twice this year, and I'm wondering if we could lease a clean room for her school to keep this down. So, my name is Bill Ravanese. I'm the Green Building and Energy Director for Healthcare Without Harm. To continue along with rich presentations and discussions, we have Chris Longchamps from Partners Healthcare and Mass General. Chris is a senior facilities engineer at Partners. He has an electrical engineering degree locally from Wentworth Institute of Technology, and he's also qualified as a mechanical engineer. He's worked at Partners for over 20 years as a senior facilities engineer. His focus over that time has been to update the MEP infrastructure in various hospital and lab buildings dating back to 1811. So I guess their buildings go from 1811 to the last one that opened, which was the new Spalding Rehab in 2013, which is a LEED Gold building. And over the years, he's managed to save $40 million in energy savings. He's currently developing an energy conservation model that can be monitored and tracked using building automation system as a continuous commissioning tool. Chris Longchamps, welcome.
It was good to see the UC Irvine guys. I mean, a lot of what you guys were saying is stuff that we were doing. So it's kind of nice to have that validation that we've been doing the right thing and looking at things. And I'm just going to kind of give you the disclaimer for this presentation. There's no rocket science in this. I'm going to give you about 5 things you can do to your lab that will save you up to 30% of your total utility costs. So a few years back, we entered into the Strategic Energy Master Plan. We finally talked to financial people into giving us some money. Okay, so we sold them on the fact that we could save 25%. So I won't read all through this, but we sold them initially that we could save 25% within about 10 years. So we started with a 2008 baseline, and we started some of our projects in 2009, mostly in earnest in 2010. At the point we got to about 2012, we had hit 25%, which was great. It was, again, I'll go through some of the measures that we did. And in 2013, we were up to 32%. So as any good organization, what they did is they said, did we say 25%? We meant 40%. We want to save 40% of your total utility costs. So they kind of raised the bar a little bit, which was fine. And we're still kind of working on that. The last numbers that we have are from our fiscal year 2013, which is what I'll kind of use now. We've still continued to save some more from there. And to put it in perspective, I'll kind of lay out the money that we spent. So we've spent about $12 million. We've received about $5 million worth of incentives. And I know there's some NSTAR people in here I'd like to thank, which have given us a lot of the money. And the thing that I'd like to say about that, too, is for all you people who are in Massachusetts, you're actually paying for an energy conservation fee for every kilowatt hour that you use. If you're not getting any incentive money back, you're losing that money. So you need to get some of that. I just want to make sure everybody understands that. So our total cash outlay is about $17 million, and our return on that investment to 2013 is about $42 million. So no question about did it pay back in a timely manner. Some of the initial paybacks were less than a year. Some of them were more than a year. Most all of them to date have been less than 3 years. Now again, it's hard to keep up those numbers, as I guess everybody would agree, but at least initially we did a great job. And I'm not going to spend a lot of time on this because I don't have a lot of time, but I'll give you the overview. There's our bar, very simply. This is how we saved the money in 2008 to 9. Like I said, we had a little bit of savings. From 9 to 13, you can see that really ramping right up. So we did a whole lot of projects in a short amount of time, and we achieved a whole bunch of savings. And I'd love to tell you, it was real easy, and all we did was implement projects and just walk away from them. And I'm going to talk a little bit about in the end about the continuous commissioning, and I know the UC Irvine guys had talked about that. I'm a firm believer that you need to watch what you've implemented to make sure that your savings stay. I mean, there's no question about it. If I turned my back on this and I left, you'd see that line just as quickly decrease over the next 5 years down to right back to where we were. So some simple measures, that you can use, and we have medical facilities and we have lab facilities here. On-off scheduling. I mean, it sounds so simple, and that's why I just want everybody to realize that there are huge savings there. More from the hospital side, we get the feedback to say, look, a hospital is 24/7. We can't turn anything off. We can't set anything back. That couldn't be further from the truth. I mean, the actual inpatient, square footage of our facility is probably less than 25%. We still have all of the support space, most of which are offices. These people are not there 24/7. Some people like to tell you that they are. They're not. There's a whole bunch of spaces that you can save a whole lot of money. So the minimum CFM set point, I know that the guys talked about that. That is absolutely huge. And for the reasons that you guys were talking about, 100% outside air in a laboratory building, with, depending on where you're getting your steam in this area or your electricity, you're probably $5 to $6 per CFM. If you buy district steam, of Trigen or one of the local vendors, you're probably even higher than that. So every CFM you can save is a lot of money. Deadband thermostats, very, very simple approach. I know these guys were talking about building automation. These building automation systems that you have now are extremely intelligent. They're little microprocessors built in there. You can almost program them to do anything. A deadband of a couple of degrees, I don't know, can anybody in this room tell when it changes a degree? Probably not. You probably wouldn't even know 2, 3, or 4, or 5 degrees. Fume hood modifications, I'm going to show you a little bit more about that, and I'm not going to spend a lot of time in here. These are some of the savings that we got. And it's just, they're big numbers. Talk about BTUs. If we assumed a 1.5% increase in our actual usage, which is pretty typical over the last 10 years for our facility, and it's just density of the same square footage, where we're using more in the same amount of space. We would have been up about 1.8 million MMBTUs. And right now we're at about 1.3. So we have a savings of about 500,000 MMBTUs. And everybody likes to talk about the greenhouse gases. It's about 26,000 metric tons. And to put that in perspective, I said, well, what does that really mean? I looked it up on the internet. I said, what does 26,000 metric tons of CO2 mean? It's essentially, it's the output from a good-sized landfill, which everybody can say, whoa. You think about a landfill and you think about the off-gassing of it. It's about equivalent, so to try to put it in perspective. The savings in energy would actually heat and cool over 5,000 homes, just for giggles, about 5,390 homes. And I tried to put it into a building. I was going to do the Empire State Building, but I didn't quite get to it. So 5.4 million square foot building. We could heat and cool that if there was such an animal, if there was a 5.4 million square foot building. The savings would be equivalent to that. So you can see that before, the blue lines were 2008. That was our baseline. Significant savings in dollars per square foot. I mean, this is substantial. Some of our lab buildings are in CNY 149. The case study that I'm going to talk about was SIMCAS. You can see we were over $10 a square foot. After we were done, we were below $7 a square foot. It's huge savings. Some of the benchmarks that you guys are probably familiar with, you talk about energy use index like these guys were talking about, kBTU per square foot. The top indicator is talking about, that's academic medical research, which is typically our facility. We're kind of split between labs and we're split between a hospital. And you're somewhere around 325 kBTU per square foot. I'm sorry, you're about 270. The labs are somewhere around 320. And you could argue back and forth exactly where they land. But before, I want to focus on the SIMCAS. The SIMCAS was over 400 kBTU per square foot, and we got that number down below 250. So it's a substantial change. These guys were saying it. Everybody's feeling it. The rates are going nothing but up. I mean, I don't think anybody's going to question that. I mean, you can ask the NSTAR guys in the room, are we going to get a 25% rate reduction in the next 5 years? And they'll be laughing. They'll still be laughing when we're all gone here, without question. So I picked a case study. It was, at the time, it was a fairly recent building. This was built in 2005. We started in earnest at about 2009. So by all rights, that should be we built best available technology. It was a VAV system. We did everything we thought would save energy, without question. About 400,000 square foot. You can see there's a picture of it. Beautiful building. The architects love to build glass buildings around here. As an engineer, not a big fan of glass buildings for the obvious reasons, but I don't have the input on that. So we looked at the minimum air changes. We implemented occupied, unoccupied. We looked at a heat recovery system to preheat the air, and I'll show you a slide on that. So the facility, like I said, was equipped with highly efficient, best available technology. It had high ventilation rates. It had continuous HVAC occupancy, extended lighting occupancy, excessive hood ventilation, and no heat recovery. So those items right there are the 5 items that we tackled. That's what we did. So we went after that, and we said, okay, ventilation rates, you guys talked about that. We did our own looking. Kind of the rule of thumb, people say 6 air changes per hour. Really, if you look at code, a code doesn't really tell you. There's a lot of recommendations. There's a lot of people that will tell you, we think it should be this, or from ASHRAE or even NFPA. There's a whole bunch of people that will make a recommendation, but there are very, very few people that will put a stamp on it that says you need X air changes per hour. And again, that can be the dilution rate like you're talking about. There maybe isn't a very good correlation between air changes and dilution. You can make a whole bunch of arguments. Again, somebody said it earlier, I could spend hours talking about that and it would still be going back and forth. We found generally they were in 7.5 to 9 air changes per hour. It's 100% outside air unit. Like I said, $5 or $6 per CFM, huge savings. Absolute huge savings. Had a DDC system in it, went in and changed set points. Looked at the balance of the distribution, tried to maintain the pressure relationships. You guys all know that we're running these labs under negative pressure, and we were done. Walked away with a minimum amount of money into this and a huge amount of savings. Air changes for offices, there are still, like we said, there's a lot of offices even in labs. Air changes typically, engineers are lazy, let's be honest. They say, okay, the VAV system, the minimum is 50% of the maximum. It's easy to divide by 2, right? So you're going to divide that in half, and you're going to come up with your minimum. Well, 50%, like these guys were saying, is still way too much. If we're talking about we're providing 6 air changes just for sensible cooling in the space, it's too much air. We do it in offices with 2 air changes. So it didn't make any sense. We went back and revisited them. We lowered the minimums again, came up with an appropriate one. Had to maintain the pressure relationship. I say that again because that's kind of key. You have to make sure that you do that. Lighting schedules, same thing. We actually tied the HVAC and the lighting schedules together so they were all singing off the same sheet. The advantage mentally for us was that if somebody goes into the space and the lighting was off, the HVAC was also in a reduced mode. They'd never know that the HVAC is in a reduced mode. I mean, let's be honest. You wouldn't know because you have more than enough cooling and heating available to do the job. However, would somebody complain if the lights are off? You bet. They're going to come in, they're going to say the lights are off, something's wrong with this building. They're going to call maintenance and say, hey, you got to get up here and fix it. At that point, when they're synced together, we know to look at the 2 of them. You've got to look at the HVAC as well. So you've got setbacks on the thermostats. Any one of the thermostats in the place will bring this thing back up to 6 air changes, 72. Everything will be 72 and fluorescent all day long. There's our VAV system. Initially, when we went in here, I didn't show a graph on it, and I know these guys did. It was the same thing. It was constant volume. There was no setback. We bought a VAV system, and they ran at constant volume. And that's just what happened. I can tell you there's got to be hundreds, if not thousands of them out there that do the same thing. And you can see, same thing on this is a week, 5 weekdays, and then the weekends. There is some occupancy on the weekend, but even labs, but still, it's not 100% occupancy. And absolutely at night, we kind of found that the 7 to 7 hours were the core hours. For some reason, researchers tend to come in late. I don't know what it is. And they tend to work late. That's the experience with what we've had. So we kind of extended that hours later. But there's probably not too many people in the building at 7. So fume hood ventilation, we had a lot of constant volume fume hoods. And we said, well, how can we reduce that? Environmental health and safety says that we have to maintain 100 feet per minute. You guys all know it's between 80 and 120, depending on exactly what your requirements are. So we said, what if we reduce the open area? I know you guys were talking about the actual closing the sash. We tried that for a long time. If it's not something that happens automatic, it's probably not going to happen. So what we did is we went in, We changed the opening of the hood by actually installing glass panels, and actually it became an improved safety measure also, because now this person has the ability to work with this panel in front of them. So they actually have a physical barrier between them. I only have about a minute here. So the heat recovery, we put in a runaround loop. It was 100% outside air and 100% exhaust. The thermal savings were unbelievable. And I'll skip to these. Here's the savings right here. So on annualized saving, FY08 is our baseline versus FY12, which is what we used, is about 4.3 million kilowatt hours a year. And the thermal savings were about 683,000, a lot of which were from reheat and from the heat recovery, from the runaround loop. So the numbers are pretty substantial. Lessons learned, the continuous commissioning. My FY12 numbers would not be the same if it wasn't for continuous commissioning. And if I could get one thing across to you guys, that's it. It would be right back where it was. We have an intern that we generated all of these energy alarms. I think we have the same picture up there too. Where we look at the VAV airflow to make sure it's turning down. We look at the heating coil to see if the reheat's leaking by. We look at the occupancy hours to see if the mechanic has overridden it. You know, we look at air handler leaking valve, simultaneous heating and cooling. We've generated, this is an old slide, but we've generated over 100 energy alarms that automatically will alert our intern and he starts to dig into it. So we have 100,000 plus points that are physical points on this system. We only have to look at the ones that are in trouble right now based on these algorithms. So that's been a huge plus for us. And I think I made it just in time. Thank you.